Hello, and welcome to Lecture 3 of this course on symmetric computation. In this lecture, first of all, I'm going to carry on with the proof of the Seyfert-Immermann theorem, which gives a construction of classes of graphs which cannot be distinguished by CK equivalents for arbitrary k, which then yields a polynomial time graph property not definable in fixed point logic with counting. And I'm going to move on from that to looking at other characterizations of the class of properties definable in fixed point with counting using rather different models of computation. We'll look again briefly at relational machines, and then we will look at circuit models. But to start with, let's review what we were looking at. We were looking at a proof of the Seyfert-Immermann theorem. So recall the construction of Seyfert-Immermann graphs. These are, they show that there's a polynomial time graph property not definable in FPC by constructing a sequence of pairs of graphs which are CK equivalent, right? The kth pair in the sequence is CK equivalent, and which are not, which are distinguished by some polynomial time decidable class of graphs. We had a look at the construction of the graphs. We start with an arbitrary graph G, and for an arbitrary graph G, we can define a graph XG, where we replace every edge with a pair of edges and every vertex with a gadget that looks like this. It has two, what we call outer vertices, for every edge incident on the vertex V, and a collection of inner vertices, and there's 2 raised to the power d minus 1 of them, where d is the degree of the vertex. One for every even-sized subset of the neighbors of V. Okay, and these ones are connected so that if the subset associated with this one, let's say for example is 1, 2, then it's connected to the A vertex for the neighbors 1 and 2, and the B vertex for the one that's absent here. Okay, in general, the A vertex for all elements of the set, the B vertex for all elements that are not in the set. The key property of this gadget is that if you take any 2 pairs of the outer vertices, you can permute the vertices within the pair, and that extends to an automorphism, the whole gadget, by a suitable permutation of the inner vertices. But you can't do it for any single one. More generally, you can take any even-sized subset of the neighbors and permute them. But really, we're interested in distinguishing the case of 1 and 2. That is the key property of the gadget. Now, the claim is that if you start with a connected graph, then the resulting graphs are non-isomorphic. Okay, that is not too difficult to prove. And the second one is if the graph has TreeWidth at least k, then the resulting graphs are CK equivalent, right? Still, we require G to be connected. And for this, we do this by a game argument, which is done, that is, we show that on XG and this X tilde G, in the k-pebble bijection game, duplicator has a winning strategy. And I will give you an outline now of what that winning strategy looks like. Before we do that, we will look briefly at what TreeWidth is and how it's used in the game characterization. So TreeWidth, many of you may be familiar with it. It's a measure, in some sense, of the connectivity of a graph. The higher the tree width of a graph, the more interconnected it is. And the lower the tree width, the more it is tree-like, right? So trees are connected graphs, but they are kind of very weakly connected, then that you remove any vertex other than a leaf and you disconnect the graph. And more specifically, between any 2 vertices, there is exactly one path. Okay. So trees are very weakly connected in a certain sense. Roughly speaking, a graph has tree width k if you can cover it with subgraphs of at most k plus 1 nodes in a sort of tree-like fashion. Okay. This is a sort of brief picture. The black circles are nodes in the graph, the black lines are edges, and the blue shapes are covering bits of the graph, and the shapes are kind of connected in a tree-like fashion, which we can formalize. And you'll see that the largest collection of nodes covered by a single blue region is this one, where it has 4 vertices in it. And therefore this demonstrates that the underlying graph drawn in black has tree width 3, or tree width at most 3. In fact, it is exactly 3 in this case. I take that back. I think this graph has tree width 2. Okay, because you could split this set of 4 nodes into 2 sets of 3 nodes without having an edge crossing them. Okay. Formally, if you have a graph, so this is undirected simple graphs, remember, so with the set of vertices V and a set of edges E, then the tree decomposition of a graph is a relation which relates the vertices of the graph with a tree T. Another way of saying this is we have a tree T, and we associate with every node in the tree T a set of vertices. Right? Now this says that on the other hand, if you look at every vertex and you look at the collection of tree nodes with which that vertex is associated by this relation D, then it should form a connected subtree of T. Right? So T is again, we can think of it as an undirected tree. But if the vertex V appears in the set of nodes, in the set of vertices associated with a particular let's say, with 2 distinct nodes of the tree, then it has to appear everywhere along the path between those 2 nodes. That's another way of stating this condition. This says that for every edge in the graph, there is a node in the tree which contains it. All right, so both endpoints of the edge are associated with this node. So we call the set of vertices associated with a node in the tree T the bag at T, the bag at this node in the tree decomposition. So the tree decomposition is really this tree T. Each node is associated with a bag of vertices. Every edge is contained in some bag, and the collection of bags with which a vertex to which a vertex belongs is connected within the tree T. Now you take the size of the largest bag, and we call that the width of the decomposition, and the tree width of the graph is the smallest value of k, such that there is a decomposition of width k. To be precise, we define the width of the decomposition to be 1 less than the size of the largest bag. This guarantees that trees in fact have tree width 1 rather than tree width 2. That's the reason for the +1 there. Okay, this is a sort of rather technical definition, and if you haven't seen tree width before, this will give you very little intuition. There's a vast literature on tree width of graphs, and if you're interested, you can look at that. We're going to use a rather different characterization of tree width, which looks rather different, but which is very useful for the purpose we have in mind, which is the characterization of tree width in terms of what are called cops and robbers games. So this is a somewhat different game from the ones we've seen before. We've seen a couple of different kinds of games, pebble games, bijection games, and so on, which are played on a pair of structures, such as graphs. This is a game played on a single graph between 2 players. One of them is in charge of a robber. The other one controls a team of K cops. The aim of the cop player is to catch the robber. The aim of the robber is to escape. And here are the rules of the game. So we have K cops. All cops as well as robbers sit on vertices of the graph. So in other words, there's a set X of vertices of size at most K, where the cops are, and there is a vertex R on which the robber is present. In each move, some of the cops are going to move. So and the cop announces them. So these some subset of the vertices x from those cops will be removed and placed in a new position. There is no requirement that there be a path in the graph for them to follow. The graph plays no role in this. These cops have helicopters, but they're noisy helicopters, so the robber knows exactly where they're headed. The robber responds. The robber is confined to moving along the edges of the graph. So the robber responds by moving from subnode, from the current position R, to some vertex S. But the path from R to S must be such that it doesn't go through one of the stationary cops. That is, one of the cops in X, which is not moving. The new position is the cops are in this position, those that didn't move, and the new positions for those that moved, and this is the robber position. If S is in this set, then the robber is caught. Otherwise, the game can continue. So this is the connection with TreeWidth. In a graph G, you look at the smallest number of cops you need to guarantee a winning strategy for the cop player. In other words, to guarantee that the robber can eventually be caught. That is a measure, again, of the connectivity of the graph, and it is intimately connected to TreeWidth in the fact that it is exactly one more than the TreeWidth. So this gives us a characterization of TreeWidth in terms of these games, and this is what we'll use in our proof of the Taillefer-Immermann theorem. Just a little bit about this theorem of Seymour and Thomas, which characterizes cops and robbers, which characterizes TreeWidth in terms of cops and robbers. One direction of it is easy. If I give you a tree decomposition of width k, it's not hard to find a winning strategy for k plus 1 cops. What you do is you place your k plus 1 cops. So the tree decomposition has width k means that every bag of the decomposition has at most k plus 1 vertices in it. And these bags form a tree. You place your cops on one bag of the decomposition, somewhere central in the tree. Now, what that means is the every vertex which is not in this bag appears in some subtree, but cannot appear in more than one, for the simple reason that the connectivity condition of a tree decomposition means that if a vertex appears in more than one bag, it must appear in all bags along that path, so it must appear on this in the bag which we have had the cops occupy. So if the robber is not caught, the robber vertex appears entirely within one subtree of the decomposition from our current position. And essentially we have confined the robber to a portion of the graph, and we move the cops to now effectively the root of the subtree in which the robber is. And this process can carry on, pushing the robber further and further down towards the leaf of the tree decomposition until the robber is caught. Okay, so that's the easy direction. The other direction is that if you have a winning strategy in the cop game, from that you can construct a tree decomposition. That requires a little bit more work, but it need not concern us here. We may as well take the cops and robbers game as our definition of TreeWidth, and that will suffice for our purposes. Okay. To make the Taillefer-Immermann, so I'm going to show you why a cop winning strategy on the graph G can be turned into a duplicator winning strategy in the bijection game played between these graphs xg and x tilde g. That's the aim. But before that, it's worth knowing that we do have graphs G of arbitrarily large TreeWidth, where you can take the cops and robbers game as the definition of TreeWidth. And an example is what I call the k by k toroidal grid. So the claim is if the graph G is a k by k toroidal grid, then the robber has a winning strategy in the k cops and robbers game played on G. What do I mean by the k by k toroidal grid? Let me draw it for you. So by a grid, I mean exactly this. This is the 4x4 grid. Right? So the k by k grid will have k rows and k columns. To make it a toroidal grid, we add edges between the top and bottom vertex of every column and between the first and last vertex of every row, so that every vertex now has degree exactly 4. That's what I mean by the k by k toroidal grid. And now I want to argue that on this k by k toroidal grid, robber has a winning strategy to escape a team of k cops and robbers, right? So k is the number of rows or the number of columns in this grid. Okay, how do we show this? The point is that at any point in the game, at most k vertices are occupied by cops. So let X be a set of k vertices. Now, the rest of the graph, apart from these k vertices, must contain a connected component with at least half the vertices of G. Why is this true? Well, first of all, consider the situation where all vertices in X are in distinct rows. A small correction. This should say, if all vertices in X are in distinct rows and distinct columns, then the graph is still connected. If all vertices in X are in distinct rows and distinct columns, then the graph is still connected. Then the remainder of the graph is still connected. To see this, imagine I've drawn in blue 4 vertices in distinct rows and columns. Now, each row is still connected because it's a simple cycle and I've only removed one vertex from it. And each column is still connected. And between 2 rows, therefore, there is any 2 rows are still connected by the common column. Okay. So, consider the case where not all vertices are in distinct rows or distinct columns. Without loss of generality, say that you have 2 elements of X in the same row. That means that the rest of the graph contains a row which contains no element of X. Okay. Look at the connected component containing that row. Now, we have a row. In this case, for example, suppose the bottom row has no elements of X in it. Look at the columns. Look at which vertices in the columns are connected to it. Well, if a column contains at most one vertex of X, or at most one blue vertex, then all the vertices are still connected to this row. So the only ones that contain things which are disconnected from this are those which contain at least 2 elements. But of course, there can be at most k over 2 of them. So for at least half the columns, at least k minus 1 vertices are connected to this row. So altogether, the connected component of this row contains still at least half the vertices. Okay, so either way, we have a connected component with at least half the vertices. Robber's strategy is simply stay in the large component. Okay, so given a position X, there is G without X contains a large component with more than half the vertices, and robber's position is in this component. The cops move to a new position. That will define a new large component, but because the large components have at least half the vertices, the overlap between these 2 large components is non-empty, which means that robber has a path from the current position to somewhere in the overlap, and that guarantees that in the next position, robber is still in the large component. And that's it. That's all I'm going to say, which shows you that on the toroidal grid, robber has a winning strategy as long as the number of cops is at most the number of rows of the grid. Okay. Now the idea is we use this strategy, the robber winning strategy, in the graph G to construct a duplicator winning strategy in the capable bijection game on xg and x tilde g. Remember, xg and x tilde g are obtained from G by replacing the vertex by the gadgets I showed you, except in x tilde g we used an odd gadget in one place. So this means that initially we can give a bijection, which is an isomorphism everywhere except at that one odd gadget, right? That's, in fact, I mean, the graphs are the same everywhere except at that one odd gadget. And duplicator strategy is to always play a bijection which is an isomorphism everywhere except at one gadget. Which gadget it is will change over the course of the game. The idea is that if we have a bijection, which is an isomorphism, so everywhere except at the gadget corresponding to V, so V now is a vertex in the underlying graph G, and there's a path in G from V to U, then we can construct a bijection which is an isomorphism everywhere except at the gadget corresponding to U, in such a way that these two bijections differ only on the vertices corresponding to the path from V to U. The idea is, and I'll just go back to a picture of the gadget. So here we are. That we are moving the inconsistency, as it were, along a path. So if the inconsistency is in this gadget, we can, as it were, fix it by swapping these two vertices and a suitable permutation of the inner vertices. That moves the inconsistency to the gadget at the other end of this path. But now we can move that out because switching two pairs, like this one and this one, leads to an automorphism of the gadget. So like a path along the original graph G, a path in the original graph G, translates in xg to a series of gadgets. And we have an automorphism which will swap both of these and both of these. So we can move the swap between these two to these two by an automorphism of the whole graph xg. That's the key idea. Okay. So duplicator, as it were, keeps a copy of this cops and robbers game on the side and treats the cop positions as the currently pebbled positions, those vertices of the underlying graph G whose gadgets have a pebble on them in the current position of the bijection game. And whenever spoiler moves pebbles, you treat that as a move of cops in the cops and robbers game, find a new position for robber, and along that path, apply the automorphisms of the gadgets to move the difference between xg and x tilde g into a new robber position, which is in some sense hidden from the pebbles. So the pebbled positions will always form a partial isomorphism, and that's guarantees that this is a duplicator winning strategy. Okay. So this essentially is the essential idea of the proof that xg and x tilde g cannot be distinguished in the K-pebble bijection game if the underlying graph G, robber has a winning strategy against K cops. Okay. So now I want to introduce to you a term I call the counting width. So you have a class of structures. Define its counting width basically as follows. For every n, look at the class restricted to structures with at most n elements. Now, once you have at most n elements, you can define the class. I mean, it's a finite class. You can define it in first order logic, or certainly in logic with counting. And you look at the number of variables you need to define the class. In other words, you take the least value of k such that the class is closed under CK equivalence. This k is at most n, right? Because if you have n elements, then with n variables, you can describe a structure completely. Okay. So you take the least value of k, the least number of variables you need to characterize the n element structures of the class. That's now a function. And the fact that every sentence of FPC translates to an infinite collection of sentences of CK really says that this function, the counting width, of any class definable in FPC is bounded by a constant. And what we have just proved is that if you look at the cipher construction based on toroidal grids, and you take a class, the class of graphs which includes xg for each g and excludes x tilde g, right? So you include xg in the class and you exclude x tilde g, then you have a class of graphs whose counting width is at least square root of n. Well, up to a constant factor, right? I mean, in the sense that what is the size of the graph? Well, it's going to be, we have 10 I took a toroidal, k by k toroidal grid that has k square vertices. I replace every vertex by a gadget. Because they were degree 4 vertices, the size of the gadget is going to be 16. So you get 16k squared. So the counting width we get is, to be precise, square root of n divided by 16. Okay, omega of square root of n. You can actually improve this lower bound to omega n, whereby instead of grids taking graphs such as expander graphs, which are sort of highly connected but with a small number of vertices. So the in effect, they have a linear lower bound on the TreeWidth, and the rest of the argument just goes through. I used the grids simply to give you an explicit construction of a class of graphs. Now, this construction gives us a particular class of graphs which is not definable in FPC and has unbounded counting width. And then we can actually use it to, I mean, it's somewhat of an artificial class, but we can use reductions. This is sort of standard tool in complexity theory to transfer the lower bound to other classes. We want our lower bound in terms of definability, so the reductions have to be definable in a certain sense. They're not just arbitrary polynomial time or logarithmic space reductions. Formally, they are interpretations in a suitable logic, and that's what I will define for you now. So suppose we have two relational signatures, call them sigma and tau. So, and let's say tau consists of the relations R1 up to R little r. Each one has a certain arity. A first order interpretation of tau and sigma is a sequence of formulas like this. We have a formula which we call the universal formula, or the formula for the universe, I should say, whose free variables are among x1 to xd. The free variables of pi I are x1 up to xd times n sub I, where n sub I, remember, is the arity of Ri. We call d the dimension of the interpretation. So the idea is the following. In a sigma structure, this defines some set of d-tuples, which we will take to be the universe of a new structure. Pi 1 then defines a relation of arity n1 on the set of d-tuples, right? It's a relation of arity d times n1 on the original sigma structure, and therefore a relation of arity n1 on the d-tuples of that structure. and so on. So we think of this as defining a set of D tuples and a collection of relations, which together form a tau structure. Okay, so this is what it says. If A is a sigma structure with universe A, then pi of A is a structure consisting of those D tuples which satisfy pi u. And for each I, we get a relation of arity Ni on B, defined by the formula pi I. This is really just taking the idea of first order formulas as not just defining a single relation, but defining a function from structures to structures. So a first order reduction of a class of structures C to another class of structures is a FO interpretation, which for any structure in C gives you a structure in D, right? And if and only if. So an interpretation such that A is in C if and only if theta A is in D. This is the usual notion of a reduction. A reduction is simply a function from a reduction from a class C to a class D is a function which takes structures in C to structures in D, structures which are not in C to structures which are not in D. Here we're just requiring that that function be given by a first order interpretation. And if it is, we say that C is first order reducible to D. More generally, we can define reductions in any logic, for example, FPC. And the point is that if you have a reduction from C to D in FPC, then we know we can transfer a lower bound on the counting width of C to a lower bound on the counting width of D. To be precise, what is the lower bound on the counting width? Well, it's given by the lower bound on the counting width of C raised to the power of 1 over D, D being the dimension of the reduction, remember. Why is this? Well, the thing is, if you have two structures in C which cannot be separated by K equivalents, and they're structures of size n, then by the translation you get a pair of structures in D which cannot be, or okay, I really should have said a structure in one in C and one not in C which cannot be separated. Then you'll get a pair of structures, one of them in D and the other one not in D, which cannot be separated by some constant times K, right? The constant being the number of variables in your reduction. But the size of the structures here that are being that we can't separate has also grown. It can be as big as n raised to the power of D. So this constant in the number of variables is taken care of the omega, and the blow up in the size of the structure shows up as this 1 over D over here. If it happens that the reduction takes structures in C to structures in D of linear size, if the blow up in size is not n to the D, but linear, then we actually get a lower bound, which is up to a constant, the same. And we had, I told you that we can get a class of structures with linear counting width if we start with a class of expander graphs and applies the CFI construction. And it turns out that we can then use reductions to establish a linear lower bound, which is as good as it can, up to constant factors, as strong a lower bound as you can hope for. We can establish a linear lower bound on the counting width of problems such as 3-SAT, XOR-SAT, 3-colorability, Hamiltonicity. And this is something you can look at, explore in the exercise classes. Note 3-SAT, 3-colorability, and Hamiltonicity are all NP-complete problems, but XOR-SAT is in fact a problem in P. But for all of them, none of them is definable in FPC, and provably so, and they have linear counting width. We'll take a pause now, and in the next part, I will start looking at other models of computation which relate to FPC.